no decimos cuándo, de sabático trabajando con Pepa y con Mariano Moles. Entonces fue cuando yo la conocí, pero entonces no trabajaba nada. Nuestra colaboración es muy reciente, de hace muy poquito tiempo, pero por introduciros un poquito a Deborah, hizo el correspondiente a la maestría en México en la Universidad de Moscú con Zeldovich. ¿Ok? Zeldovich. Y ahí es donde empezó a tener contacto con los agujeros negros o hoyos negros, como dicen en México. Después hizo el doctorado en la Universidad de la Sorbona en París y es profesora del más alto nivel en el Instituto de Astronomía de la UNAM en México. Tiene más de 250 publicaciones en astrofísica, además de primera o segunda autora. Eso se dice al menos en la ADS. Y ha estado trabajando principalmente en los procesos físicos que ocurren alrededor del agujero negro, en el estudio tanto fenomenológico como modelando de alguna manera, y no solamente las condiciones físicas y dinámicas de las regiones alrededor del hoyo negro, agujero negro como decimos aquí, también estuvo durante muchos años trabajando en variabilidad de núcleos activos, y un trabajo que ha seguido durante mucho tiempo, que ha sido ver cómo afecta el entorno en esos agujeros negros, en Seyfert, en cuásares, en diferentes tipos de actividad. Ha escrito, además, al menos que yo sepa, 2 reviews, uno en el Annual Review sobre cuásares y otro en el New Development in Black Hole Research, y también tiene muchas contribuciones en un libro que se publicó con motivo del 50 aniversario del descubrimiento de los cuásares. Ha dirigido y codirigido 21 tesis, no sé si más, desde las que yo tengo aquí, de licenciatura, maestría y doctorado, y en 2010 recibió el premio Ciudad Capital, ¿cómo se llama esto? Eberto Castillo, algo así, otorgado por la Secretaría de Ciencia y Tecnología del Gobierno de la Ciudad de México, conjuntamente con la Academia Mexicana de Ciencias, y recientemente, este año, en 2016, ha recibido el Premio Universidad Nacional de México por todo el reconocimiento a toda su trayectoria científica y de docente. ¿Okay? Y bueno, yo estoy encantada de que Deborah haya podido venir de aquí una semanita y os va a hablar de
bueno, miren, quizá más adelante a lo largo de mi charla les quede claro por qué puse este loco título. I'm sorry. Switch. Yeah, this crazy title will explain itself after, I hope. Well, mainly, I will talk about AGN. There is the so-called unified model, which was originally proposed actually for Radio Loud AGN by Urrin Padovani. And this has to do with the large scale jets and so on. And of course, it depends on the viewing angle. You can see jets, or if you look like this, you can see a blazer if you look directly towards the jet, etc. Okay. Then, in 1996, Antonucci proposed a unified scheme for the inner parts, particularly of Seyferts. And he said, here you have the black hole, here the emission, here you have the accretion disk, the emission of broad lines, then further out you have a dusty torus, and of course, if you look from here, the dusty torus can obscure totally the broad line emitting region, and you see a Seyfert 2 galaxy. That is a galaxy that has only narrow emission lines, which are not obscured by the dusty torus. And if you look from other angles, you can see the broad lines. And so he went as far as to say that all Seyfert 2 galaxies, that is galaxies with only narrow lines, are obscured Seyfert 1. And this became a dogma that nobody questioned, but we questioned it. So the story began a long time ago, 1,000 years ago, in 1999. We looked for the environment of Seyfert galaxies, and we found that close environment. What is close environment? Like 100 kiloparsecs. And we found a different environment for Seyfert 1 and Seyfert 2 galaxies. After that, there were many papers that confirmed these findings, and at that time, in 2002, we proposed an evolutionary model for Seyfert galaxies in order to explain this difference in environment. What was the difference in environment? The difference in environment was that Seyfert 2 galaxies had statistically more often close companions, I'm talking of same mass companions, not mosquitoes, same mass galaxy companions, more, and we compared with isolated galaxies, and Seyfert ones were like isolated galaxies, more or less, not this kind of, let's say, excess of close companions. Okay? At that time also, I have to say, in 1999, Sanders proposed that ULICs, which are the ultraluminous infrared galaxies, evolved into quasars. That is, there was a big merger, and the big merger produced a larger black hole and lots of dust that covered the whole thing, and with time, the evolution of the quasar swept away the dust, and one could see a quasar. This was very nice, a very nice proposal, because soon after, people started looking, for example, in the optical at ultraluminous, and they found indeed often two active nuclei, two Seyferts, and so on. So it was very nice. So we proposed also that the evolution could be induced, maybe not only by merger, but even by close encounters. And so we said, first you get a starburst, circumnuclear starburst, which I know I made a mistake. Sorry. Which evolves into how? If you have originally a black hole in the nucleus, if it's originally already something with a black hole, either by a merger or close encounter, you get the same effect, a circumnuclear star formation, very strong starburst, and then here I made a mistake. It would evolve first into a Seyfert 2, that is something obscured with a lot of dust, and then as time goes on, by the AGN, by the nucleus, and also by the evolution of the Wolf-Rayet and the OB stars, they sweep the dust, and finally you get to see the Seyfert 1. I made a mistake here. All what I said is written here. So the perturbation, by the way, this is important to say, is supposed to cause, well, there is an axisymmetrical, non-axisymmetrical perturbation, and this also drives gas into the nucleus. So first you have a composite Seyfert 2 with a starburst nucleus around it, and then it evolves. It can be an obscured Seyfert, which may be seen depending on orientation as a Seyfert 1 or a Seyfert 2. In this stage, we can speak of a unified model, that is, something that depends on orientation. Now we know, by the way, that there are also true Sifra2s, that is, they don't have a broadline region. They are born like that. Probably, or this has been said, suggested, because there is not enough accretion rate. The accretion rate is so low in these cases of Sifers that the broadline region is not formed. So here it's written correctly. The interaction produces starburst, then a Sifr2, then a Sifr1. So, this I already said. Now, what has this to do with the environment? Okay. This can explain the difference in environment because we said when the close companion is near, whether it's bound or it's a flyby, it doesn't matter. It is the moment where you see a Cipher2. And then as time goes on, what time it's like 10 to the 8 giga years. Am I correct? I think so, yes. The interesting thing is that the time for the evolution in such a way that the torus, or most of it, a lot of obscuring dust, is swept away, is the same as the time required for either a merger or the flyby to go away, okay? So, a Cipher2 is seen still with nearby companions. And by the time you can see a Cipher1, the interaction is finished, the flyby has completed, and thus you don't have companions. This is obviously all statistical. You have to use a lot of... Okay, now, we thought we could study the incidence of nuclear activity in pairs, close pairs. So we chose some close pairs which we had studied before, with other reasons, etc., etc. Even with Jack Sulentic and a student of mine, Hector, what's his name? I don't remember. Hernandez Toledo. Okay, but here we chose close pairs, close 100 kiloparsecs, similar mass, and different morphologies, because we thought we could disentangle. This is very hard. You have the perturbation, but you have the morphology, the mass of the bulge. It's very complicated. Anyway, it took a long time. Evidence of tidal triggering was studied before by some people, but they didn't differentiate Cipher1 from Cipher2 to see the stage of the evolution. In this work, we used 385 galactic spectra from SDS, from Sloan, and in the local universe of all these close pairs of different morphologies. Okay, close also meant a difference in radial velocity of 1200 kilometers per second. Okay, so for optical activity, well, these are details. We extracted masses from the two mass, K-band. Morphological classification was used using the usual, but we also did our own visual inspection, okay? And we compared with our own, because there are many, one from Lourdes here, Hernandez Toledo has another one, but we had already chosen a sample of isolated galaxies. Isolated is not the same as field galaxies. Some people compare with what they call field galaxies, but we selected a sample of rigorously isolated galaxy according to a certain definition, which is not so different from the definition used by Lourdes' student, former student, which I don't remember his name. Sorry. Eh? Sí, Sabater. That one. Exactly. It turned out not to be different. Okay, but we wanted to compare our own data with our own treatment, with our own criterion, just for methodological reasons. Okay, so we prepare diagnostic diagrams for all types, S plus S. Here you can see that the morphological type is very important. These are AGN and these are H2 galaxies. And when you go to late morphological types, you get more starburst or H2 galaxies. This is something very well known. Okay, but after a certain mass, this is a log stellar mass. After 10 to the 10 mass, stellar mass, you do see a difference. That is the AGN fraction in pairs, which I show in blue, and of course I show colors. I am very honest. I show errors. The AGN fraction in pairs, which I show in blue, compared to the fraction in isolated galaxies, which I show in red, shows a higher incidence of AGN. But this happens only for high stellar masses. Okay? Later on, Treister et al. In 2012 showed that AGN triggering due to the development or due to environment is dependent on luminosity. So it's correct. Okay, so the main results of that work were very difficult to disentangle environmental effects from morphology and luminosity. The frequency of incidence of AGN whatever, Liner, Seifert, etc., is the same in pairs, except as isolated galaxies, except for high mass galaxies. But very interestingly, in all our sample, we found Liners, tons, we found Seifert-2s, but only 4 objects, 1% are type 1, okay? Compared, 1% as compared to 4% in our own sample of isolated and 20% in field galaxies. So this is not what the unified model scheme would predict. It is a very low number for Seifert-1 galaxies. And this is not in agreement with the unified scheme. In our context, we see an initial approach of another galaxy. I'm sorry, 1 giga-year. Well, I'm crazy. I thought I was telling something stupid. Not enough time, that is about 1 giga-year, and this is explained in this paper, has elapsed for a Seifert-1 to appear after their interaction, okay? And after 1 giga-year, you can see the Seifert-1, but the companion is gone, or there is a traceless merger, one of the two. Now, in 2014, Villarroel and Korn published a very nice paper in Nature. And you see this plot is theirs, Villarroel and Korn. So they plot the type 1 to type 2 ratio against distance, okay? This type 2 is crazy. I'm sorry I made stupid plots because my students didn't help me. I made it all by myself. And it's very difficult for a person like my age to do everything by yourself. You need slaves. Okay, but anyway, in any case, you can see that for small distance, you have more. The effect is the same. The type 1 fraction increases with neighbor distance, which is more or less what I am telling you. It's consistent. Bueno, now, another work we made, no, there is a person, Moshe Elitzur, who is a specialist on dusty toruses. He started with star formation, and now he applies everything he knows about dusty toruses to AGN. So he has developed a model in which Cifred 2s become Cifred 1s. That's his model. Due to intrinsic causes, due to the dusty torus and winds and a very complicated theoretical model that I don't understand yet because I'm lazy and I didn't read very well. But he acknowledges that there is an environment, he called this environmental evolution, whereby a type 1 becomes, what is this? I me hice bolas. Type 2, no, ufa. I'm very, very sorry. It's the other way around. A type 2 becomes a type 1. No, you know what? Let's forget about everybody else's work. Now I will talk about our work. Another work, which is around the same topic, we made a mid-infrared spectroscopic study using Spitzer data of Cifred 1 and Cifred 2 galaxies, both isolated and in interaction, okay? Yes, Elitzur was part of it. So, we said, the presence of a close neighbor produces a steady inflow of gas and dust into the nuclear region, and thus, we thought, it forms a smooth dust distribution. So the dust distribution is expected to be smooth when you have a close companion. So in the final stages, the perturber is probably gone or merged, and much of the dust nearest to the nuclear region has been destroyed or swept away by the winds, and the dust that is left over cools and clumps. So you have what they call a clumpy torus. So a Cifred 1, we predict, should be observed at this stage and should have a clumpy dust distribution. So we made an analysis, we measured the following a model by Siroki. We analyzed the data in the mid-infrared, and we measured, my student, Sandro Mendoza, measured all the silicon and PA lines which are related to AGN or to star formation, depending on the fact that they are in emission or they are in absorption. Okay? mainly 10 and 18 microns. Okay? So this is more or less copied from Siroki. Ciphered ones are seen here in triangles. Yeah? This is a plot of 18 versus 10 microns. And cipher 2s are seen as circles. There is a differentiation, of course. But more interestingly, this is a small sample. We are working on a larger sample. That is, I need a slave to finish with the data in a larger sample because Sandro went away from astronomy to make money. But let's return to astronomy. So this is very interesting. Let me explain. These are cipher 2s in interaction, okay? What you see in blue is spectra dominated by Pa, polyaromatic hydrocarbons, large molecules associated with star formation. These are cipher 2s in interaction, and you see that the vast majority of the dust emission is dominated by this Pa. As time goes on, well, according to our model, you would see the transition, which is cipher 2 that are isolated. The galaxy went away, the companion. And then you see the distribution is more or less the same continuum, which is the yellow, and Pa, which is the blue. Now, time goes on, okay? We say the torus, this is another thing I didn't explain. The red is smooth, and the black is clumpy. This is the geometrical distribution of the dust in the torus. So at the beginning, most galaxies have a smooth torus dominated by Pa. Okay? Then in the transition, smooth and clumpy torus is the same. And Pa or continuum is more or less the same. Time goes on. The flyby goes away, the companion goes away, or as I told you, there is a Traceler merge. I don't care. You have more or less the same number of smooth and clumpy, and more or less the same number of continuum and Pa. But when you look at the isolated ciphered ones, which is the last stage of the evolution in our model, you see that they all have clumpy torus, all the ciphered ones, and moreover, the emission is continuum dominated. So it's a nice thing. So this supports our proposition. This is the point, 3 gigayears to have a ciphered one. Okay? And next, we studied galaxies in groups, compact groups, very inspired by an initial work of Johnny and Heli. Her last name is, I don't know what, Martinez. That's it. Okay. Now, the previous studies of galaxies in compact groups were for the local universe. Very important, the work of Martinez and Choni. Now, the new sample, we wanted to cover a larger range of redshift. Okay? So they adapted Higson's criterion to the whole SDSS database and compiled a sample of more than 2,000 compact groups. We selected this number of groups and this number of galaxies using multi-frequency data in a much larger range of redshift. So we use Galax and NUV for ultraviolet, Sloan for optical, 2MASS for infrared, and WISE also. So this is the largest multi-wavelength compact group sample to date. Okay, very nice. This was done mainly by a postdoc of mine, a Greek postdoc, Theodoros Pitsakis. Okay, we also tried to avoid biases, always obviously selection biases. So this is Malmquist bias, this is the upper limit cutoff, and we took galaxies here. And we divided into bins in order to compare apples with apples, bananas with bananas. Okay, main results. The AGN activity, we studied young and old groups, dynamically young, dynamically old. Yes? So, galaxies in dynamically old groups are more likely to host an AGN at any given mass, stellar mass. But in dynamically young groups, we see no enhancement. Yes, no enhancement of AGN activity. I want to show you this finally, which I made myself without slaves. And this is very nice because it shows the incidence of AGN is linked to high galactic stellar mass. If you look at low mass galaxies, you lose this. You don't see any enhancement due to any environmental effect. Okay? Now, it is enhanced starting with a different threshold. This is the sample of isolated galaxies, our sample. Okay? And you can see here, this is the threshold where you start seeing enhancement, AGN. This is the case for interacting pairs, and the threshold is slightly different. Starts for less smaller stellar mass, and this is the threshold for dynamically all groups. So the effect is stronger. And what? Moreover, we started looking for Seyfert 1 galaxies. Now, in compact groups, we also find 1%. This coincides, if I'm not mistaken, with your result with...
Pero solo 2008 is 4% in Higgs compact groups.
4%?
Yeah.
This is anyway of Seyfert 1, not 1 point something. Pure Seyfert 1. Okay, bueno. Now, could they be dust obscured, our Seyfert watts that are so few? Well, no, because we also use the Mearwise color diagnostic. So it's not the case. Now, if we would talk about orientation and obscuration only, which is the unified model, we should see Seyfert ones much more often. about 20% in the local universe according to Ho. And this is absolutely not the case. So our general conclusion is that the unified model is not enough. It may be relevant, that is the combination of obscuration and inclination may be relevant in determining in a certain stage of the evolution, because we have obscured nuclei. But it's not enough to explain everything. It has been proposed that low accretion leads to the absence of a broadline region. And the compact groups host only low luminosity AGN. The gas depletion in the compact groups can be due to past star formation, winds, and tidal interaction, which in compact groups occurs several times. And this leads to lower accretion rates. Okay, the conclusion is that low redshift, the fraction of AGN increases, but the overall activity drops. I don't know why I have to give the conclusions by Elitzur. He gave a talk recently in a meeting called Hidden Monsters. He says unification this is something I copied. Unification is alive and well, but with realistic qualifiers. You have to take into account the type 1-2 intrinsic differences, uncovering factor, the clumpiness of the torus, evolutionary effects, environmental obscuration, the torus structure, etc., etc. So we say that the unified model is not good enough. It is only something that can happen in a certain stage of evolution. So it might be a question of semantic. It is okay with many conditions, or it is not good, as you like it. And I think this is all. Yes, this is all, because I have no more. Thank you. Any questions? No, qué bueno. Bueno, gracias. Quiero decir, muy contenta de estar aquí. Esta es mi segunda casa. Okay. Yeah. Speak up. Más fuerte.
Okay, you have more than 1,000 groups.
1,007.
Yes.
Yes, and all the galaxies have information about the spectroscopy.
Yes.
Then you have a huge.
Yes.
The statistic is really more significant.
Exactly. Because the others are very small samples. Ahora te enseño. Yes. We have a lot.
Have you studied the difference between young and old groups?
Yes.
If you have more transformation or
Yes.
kind,
Yes.
Some relation between the activity of the galaxies
Yes.
and the type of group, young, old, or something like that?
Yes, sure. There is. Well, there is a strict definition, dynamical definition for young and old, which I don't have here. But, ¿qué estoy haciendo? No. But, we published 2 papers. In the first one, we spoke about the induction of AGN activity. And in the second one, we spoke about the the effect on star formation, not only around the nucleus, but in all the galaxy. Unfortunately, I don't have information here in this talk about the second paper, but I can tell you what I remember, okay? In dynamically, old groups, you don't see such a clear enhancement of young stars, of recent star formation. In dynamically young groups, you see more recent star formation. About the evolution of the stars in the whole galaxies, if I remember correctly, in old groups, you see star evolution statistically, which is not so different than, well, I wouldn't say isolated, but groups of galaxies, let's see. That is, the effect on star evolution is more important in young groups. That is what I remember from the second paper. Yeah. Pepe, hola.
This is very interesting results. I'm wondering whether, because the rate of interactions sometimes in groups is not that high as we expected, but I was wondering whether in the alone filaments or, how you explore the role of the environment at larger scale on the rate of safer 1 to safer 2?
Yes. Well, the point is, at larger scale, we didn't explore. We explored, but I will show you something. We only study close environment, that is 100 kiloparsecs. But the paper by Villarroel and Korn in Nature, they explore larger distances. What they find is that the type 1 fraction increases with the neighbor's distance. That is, when you have a close neighbor, you see more C-fetus. And when the neighbor, I say, goes away, but the distance increases, and this is up to, well, not so much, 400 kiloparsecs, it's not so much, but then you start seeing a higher fraction of Seifert ones. But the study of what happens in filaments or things like that, this is something we didn't study. Because in our case, it's very abrupt. When you see a single galaxy or isolated with a Seifert one, if a merger occurred, there is no trace. We looked for plumes and things like that in the radio, nothing. It's like the evolution of quasars that Sanders proposed. Okay? First, when you see the merger, you see the Euler, tons of dust, etc. Then, sometimes in the intermediate phase, you see two nuclei, two Seifert nuclei. And as time goes on, they merge, and finally you find a quasar or a radio galaxy or whatever. ¿Anchón? ¿Me dijiste hola o levantaste la mano?
Deborah, what kind of AGN do you have in these groups? Okay, is low luminosity AGN?
Low luminosity.
Always low luminosity.
It's always low luminosity.
Even the safer ones are low luminosity.
That's right. So this is something that also affects. Yes. We have low luminosity and also more or less, except in the last paper of compact groups, local universe. Yeah. Ah, ya. Mira, tú eres Lourdes, ¿no? Que ya ni veo. Hola, querida. Same here.
For this nice talk, very covering many aspects. I don't work nuclearized. When you say dynamically young or old groups, you are speaking about the velocity dispersion. So you mean high velocity dispersion, you consider it younger or in low older?
Younger is low velocity dispersion.
Okay, so you consider the increased velocity
Ah,
dispersion.
chingos. Creo, porque mira,
Yes.
me hago tantas bolas. Espérame, déjame pensar en español, por favor.
Younger is low velocity dispersion.
Younger is low velocity dispersion. Yes, exactly. Sí. Younger. This is young.
So Stefan's quintet would be older, right?
What?
Younger. Oh, okay. It's not very intuitive for me, this dynamic.
No, for me also. No. Johnny knows more.
So that's what's just to understand. And just a comment, but you probably know that after the comparison between isolated galaxies and compact groups that Pepe Sabater made in his during his postdoc, he made a paper. I'm not participating in the paper.
Yes.
He's studying 2,700 galaxies in the Sloan. So he studied the full environment,
Yeah.
central star formation, mass, and three environmental parameters.
Yeah.
He didn't distinguish between cipher 1 and 2.
That's the point. That's why I
He
wasn't.
separated kind of, so his conclusion is that environment is an indirect trigger of nuclear activity.
A ver, otra vez. Environment what?
Is not
Is-
direct, doesn't play a direct role
Yeah.
in terms of how does it contribute to the gas.
Yes.
But I thought it would be worth
Yes.
checking because he calculated the environment, three environmental parameters for the 207,000 galaxies in the Solar System. In this sense, it's statistically very valid.
Oh, yes, it's important. Well, you see, yes, I would agree in general because environment does not have a direct influence except when it becomes a very close environment. That's my point. And now, many people do not differentiate between CFET 1 and CFET 2. But when you do that and you look at it closely, it's when you can see some influence. But it is an influence of the very close environment. At the nearby distance sufficient enough to cause a tidal perturbation. Not to speak of a merger, of course it influences. Mm-hmm. So that's my point.
So he finds this one-to-one interaction to be more relevant in the case of high mass.
Oh, absolutely, yes. Yes, from 10 to 10. Stellar mass. Yes, absolutely. Okay, thank you.
Gracias.
Gracias.